Chemistry 3111. This is where we ended off last time. We finished up section 12.2, and now we're going to take a look at section 12.3. And the good news is that section 12.3 is nothing more than a review of the reactions that we've already learned in Organic Chemistry 1, and the ones that we also took another look at in chapter 11. Anything that deals with making an alcohol. So anything that deals with making an alcohol that we looked at in previous chapters. So it says here that alcohols can be synthesized from an alkene. How do we do that? We do that by an addition reaction, and we can either do an addition reaction in a Markovnikov fashion, and these two reactions are Markovnikov addition of water. Now, how would I do the Markovnikov addition of water? If I can, I will always just seek to use dilute acid. So it says here dilute sulfuric acid. If you were to just write H3O plus, that's totally fine. It's the same thing. And you should be able to draw the mechanism of that Markovnikov addition of water using dilute acid. Now, if you had carbocation rearrangements that you wanted to avoid, you would use oxymercuration followed by demercuration. So that's mercuric acetate in water. And then in the second step, you treat it with sodium borohydride. And again, the reason that we do this is to avoid carbocation rearrangements. And then if I wanted to do an anti-Markovnikov, so anti-Markovnikov addition of water across a double bond, well, for that I would use hydroboration oxidation. So those are all reactions that we covered way back in previous chapters. Again, just remember that acid catalyzed hydration yields Markovnikov addition. You really need to know that. And you need to know that hydroboration oxidation yields anti-Markovnikov addition. And of course, you also have to know the conditions for a Markovnikov addition of water when you want to avoid carbocation rearrangements. But again, these are things that we saw in Organic Chemistry 1, and we also reviewed them in chapter 11. All right, well, with that in mind, let's take a look at some practice problems here. These, really go all the way back to Organic Chemistry 1. It just says identify the reagents that you would use to accomplish each of the following transformations. Well, if we start with this molecule here, so this is 1-bromo, 1-methylcyclohexane, and we want to convert it into this cyclohexanol derivative. So this would be 1-methylcyclohexanol. Well, this is a tertiary alkyl halide, and so we're going to have to do an SN1, or we're going to do a substitution reaction, which will occur via an SN1 mechanism. So all we need to do is put it in a polar protic solvent like water. That's going to cause the leaving group to leave. It's going to generate a tertiary carbocation, then water will come in as a nucleophile, and then it will undergo deprotonation to form the alcohol. Again, that's just an SN1 reaction. So again, this is a review. In B, we're taking a primary alkyl halide. All right, for this, we're going to need a good nucleophile, because here, if we're starting with a primary alkyl halide, we're going to want to do a substitution reaction, but this is going to occur via an SN2 mechanism. And so for that, we're going to use hydroxide. Hydroxide is a strong base, strong nucleophile, but since this is a primary alkyl halide, we're not going to have any elimination. And so we're only going to get the substitution. And so we would want to use hydroxide. Now, if you just write hydroxide, when you're practicing at home, I'd say there's nothing really wrong with that, because in organic chemistry, we like to leave out cations or spectator ions a lot. But if you want to write the whole reagent, I would write sodium hydroxide like that. So again, hydroxide is going to act as a nucleophile. It's going to attack the alpha carbon. You're going to get the loss of the bromide as the leaving group, and you end up producing that primary alcohol. The next one, we're starting out with an alkene. So this is 1-methylcyclohexene. And if you look at the two carbons in that double bond, you see that only one of them has a hydrogen attached to it. And you see that in the final product, you have two hydrogens attached to that carbon. And so the rich are getting richer, aren't they? The rich get richer, right? And so just based off of that, we know that this is a Markovnikov addition of water across that double bond. Now, when we add the proton to the alkene, we produce the carbocation, and we produce a tertiary carbocation, which will not undergo rearrangement. And so all we would need here is dilute acid. You can put H3O plus, and if you want to write dilute below it or something like that, that's totally fine. You don't have to put that in there. Okay, and again, that's a mechanism that you should be able to draw, right? You should be able to draw that mechanism as well pretty quickly. The next one, if you look at this carbon, it's got 2 protons on it, and it still only has 2 protons on it in the final product. Therefore, the rich are not getting richer here. This is an anti-Markovnikov addition of water. So anti-Markovnikov addition of water. And I guess I should have included that the last one was a Markovnikov addition of water. Anyhow, there we go. So how do we do the anti-Markovnikov addition of water? Well, there's not a lot of room above the arrow, so we'll write it over here. In the first step, you're going to treat it with borane in THF, right? That makes the borane THF complex. And then in the second step, you treat it with hydrogen peroxide and sodium hydroxide, like that. And the last one is the Markovnikov addition of water across a double bond. However, here we want to avoid a carbocation rearrangement. All right, if we were to just take this molecule and treat it with dilute aqueous acid, I'll just draw an abbreviated mechanism like this, we would end up producing this carbocation, right? We'd end up with this carbocation, which would undergo a 1,2 methyl shift, okay, to produce a more stable tertiary carbocation. So we want to avoid that. And the way that we avoid that, and we spoke about that on the previous slide, is that we use oxymercuration, demercuration. So what are the conditions for oxymercuration, demercuration? And you have to have these memorized. The first step is you treat it with mercuric acetate and water together. And then in the second step, you treat it with sodium borohydride. Let me just highlight before we move on to anything else that the first 3 reactions on here, I would expect you, see A through C, I would expect you to be able to draw the mechanism for any of these, the SN1, the SN2, or just the Markovnikov addition of water using dilute aqueous acid. Now, the other 2 mechanisms, the mechanism for hydroboration oxidation and the mechanism for oxymercuration, demercuration, you don't have to draw these, okay? I'm not going to ask you to draw these mechanisms. I probably won't ask you many questions about the actual steps of those mechanisms. However, if you've never taken organic chemistry with me before, and I think that most of you have, but if you haven't, let me remind you of something. And that is that the greater understanding that you have of reactions like these, what I mean is the more you understand the mechanisms, and they are presented in our textbook, the easier it becomes to understand, why do we get syn addition of the hydroxyl and the proton when we do hydroboration oxidation, right? It gets easier to understand why we get anti-Markovnikov addition of water if you understand the mechanism for this reaction. Again, let me repeat. I'm not going to ask you about the individual steps, but the more that you understand them, the better or the easier the course becomes. If you think about any class you've ever taken in your life that you thoroughly enjoyed, and I'm sure you've all taken some class in university or college or maybe even in high school that you liked, they're usually courses that you understand what's going on. And so the greater your understanding, the more rewarding and the more fun organic chemistry becomes. Well, let's move on to some new reactions. And we're going to talk about preparation of alcohols by reduction. So by reduction, right? You might remember the old acronym from general chemistry: oxidation is losing, reduction is gaining. That's oil rig. Or the other one is Leo says Gur loses electrons, oxidizing gains electrons, reduction. So it says here another method to prepare alcohols is by the reduction of a carbonyl. Now, what is a carbonyl? This is just a review question. Everybody here should know what a carbonyl is. Carbonyls are found in functional groups like ketones, aldehydes, carboxylic acids, esters, amides, and others as well. But a carbonyl is just when we have a carbon with a double bond to an oxygen. That is a carbonyl. Okay, nothing more than that. Again, we see carbonyls in, I'll just give you a couple examples. We see carbonyls in ketones. We see carbonyls in, let's say, a carboxylic acid. And I'm not going to go on from there. But again, carbonyls show up in a whole holy host of functional groups. So reductions involve a change in oxidation state, right? Oxidation is losing, reduction is gaining electrons. And so in order for us to determine, what the change of oxidation state, we have to be able to keep track of electrons. Now, if you think about determining oxidation states, which is something you would have done in General Chemistry 1, and I know that you did it because I teach General Chemistry 1 all the time. You think about an element like oxygen. You know, why does it form oxide, O2 minus? Because it likes to gain 2 electrons. It likes to become isoelectronic with a noble gas. Now, there are exceptions, like in a peroxide, but if you remember, and what I'm getting at here is that you learned how to determine oxidation numbers of a whole bunch of main group elements, and you also looked at oxidation states of some transition metals. However, one element that gets left out of general chemistry is carbon. I mean, I've taught general chemistry enough to know that carbon basically never comes up in terms of its oxidation number. And we're going to learn how to determine the oxidation state of a carbon today. And the way that we do it is, it says here that each atom is assigned half of the electrons it's sharing with another atom. Well, that, is how we calculate formal charge, okay? So if we wanted to calculate the formal charge on a carbon and methanol, for example, sorry, I'm getting a little bit ahead of myself here. I'm getting overly excited about talking about oxidation state, but just reviewing here. This is a review. So what I'm talking about right now is formal charge. Again, I get a little bit ahead of myself here. So how do we calculate the formal charge, right? We have 4 valence electrons for carbon because it's in group 4A. Subtract 4 sticks and 0 dots. So it's got a formal charge of 0. However, it does not have an oxidation state of 0. So the way that we determine the oxidation state is quite a bit different from the way that we determine the formal charge on a carbon atom. So here we go. It says, to determine oxidation state of a carbon atom, we imagine the electrons in a bond as a lone pair, and that pair of electrons will go to the more electronegative atom. So you remember I told you before, I told you in Organic Chemistry 1, you know, it's a good idea to remember, and when I say a good idea, I mean it's necessary for you to remember or memorize a few electronegativity values. So here's an example of where maybe the memorization would come in handy, but all you really need to know is the trend, right? The electronegativity increases as we go from left to right across the second period. Anyhow, so what happens when we calculate formal charge? Now, I know I taught you the formula, which is just valence electrons minus sticks minus dots, right? So, and in case you didn't take, you know, organic chemistry with me, right? When you calculate the formal charge, you say 4 valence electrons minus 4 sticks, right? Every bond counts as a stick. So we subtract all the sticks, and then we subtract all the dots. There are no dots on that carbon. So 4 minus 4 minus 0 gives us a formal charge of 0. Essentially, what we're doing is we're breaking the bonds homolytically, right? We're splitting everything up evenly. So you can think about the carbon as having 4 electrons surrounding it. So if you take 4, right, and you subtract the 4 electrons that are surrounding it, same thing. What do you get? 0. It's essentially the same thing that you're doing here. It's just done in a different way. So when you break the bonds that are on a carbon in which you want to calculate its oxidation state, what you do is you break them heterolytically. Now, what does it mean? It might sound scary, like, oh no, how do I do that? All you do is you break the bonds, right? And there's 4 bonds to the carbon. There's one here, there's one here, there's one here. And we'll talk about the carbon oxygen in a second. All 3 of those bonds between carbon and hydrogen, who's more electronegative? Well, carbon has an electronegativity of 2.5 and hydrogen has an electronegativity of 2.1. So the answer is carbon is more electronegative. So we take the electrons from this pair, from this bond, this pair from this bond, and this pair from that bond, and we put them all on the carbon. So here's one pair, here's the second pair, here's the third pair. There's one more bond, isn't there? There's the bond between carbon and oxygen. The oxygen already has 2 lone pairs, right? But what we do is we take the 2 electrons in here and we put them on the oxygen. Why? Because oxygen is more electronegative than carbon. So when we're calculating the oxidation state, and I'll use my blue pen here, it's as if the carbon is surrounded by 6 electrons. So the way that we calculate its oxidation state is we say 4 valence electrons, right? Because carbon is in group 4A, subtract 6 total electrons that are around it, and its oxidation state in methanol is actually -2. Okay, so again, the formal charge on the carbon is 0. However, its oxidation number, or its oxidation state, is a -2 charge. All right, now we could do the same thing for a whole bunch of different compounds. And if you go from methane to methanol to formaldehyde to formic acid all the way up to CO2, you see that carbon can adopt so many different oxidation states. It can go from -4, it can also be -3, -2, -1, 0, 1, 2, 3, 4. Okay, So what happens is that if we're looking at an oxidation reaction in organic chemistry, what that means is that the oxidation number of the carbon is going to increase. Like let's say I took, let's say I took methanol and I converted it into formaldehyde, right? That would be considered an oxidation reaction. However, if I took formaldehyde and I converted it into methanol, you're going from 0 to -2, right? Its oxidation state, the carbon's oxidation state is decreasing. So that would be considered a reduction reaction. Now, sometimes oxidation and reduction reactions are very apparent, right? It's very obvious what the heck is going on. Other times it gets a little more difficult. So that's why it's imperative that you're able to calculate oxidation state. Let me show you a couple more here just to kind of cement the concept. Let's look at CO2, right? Oxygen is more electronegative than carbon, isn't it? So let me just start by drawing in the lone pairs that are on the oxygen, okay? Now I'm going to draw the carbon. I'll put one oxygen up here and I'll put one oxygen down there. Now, both oxygens already have lone pairs on them, so I'll put those in there. Now, what about the bonds? I have a sigma bond and a pi bond here, and I have a sigma bond and a pi bond down here. Each one of those bonds has 2 electrons, and since oxygen is more electronegative, it's going to take all of those. Let me be consistent with my coloring here. So 1, 2, 3, 4, right? 2 electrons from the sigma, 2 electrons from the pi, 1, 2, 3, 4. So now your carbon is surrounded by nothing, right? So if we're calculating the oxidation state of this carbon, it's going to be 4 valence electrons, subtract 0, nothing, no electrons around it. 4 minus 0 gives you plus 4, like that. Let me show you another example. Let's take a look at the methane molecule, because we look at a lot of hydrocarbons. In fact, we'll do an entire chapter where we talk about, in Organic Chemistry 1, we did an entire chapter where we talked about alkanes. Same rationale here. I'll draw the carbon. It's surrounded by 1, I don't have a lot of space here, 1, 2, 3, 4 hydrogens. Each one of these bonds has 2 electrons in it, doesn't it? Well, carbon is more electronegative than hydrogen, so it's going to take these 2 electrons, these 2, these 2, these 2, and these 2. So when I'm calculating the oxidation state, I have 4 minus a total of 8, and I get -4. Oops, -4, just like that. All right, so that is how we calculate the oxidation state of a carbon. And, it's something that gets left out of General Chemistry 1. Give me a thumbs up if you just follow me on the concept of oxidation state of a carbon, because you're going to need to know it in order to evaluate whether an oxidation or reduction reaction is occurring. And of course, I'm going to ask you about it on quiz 12. All right, thanks, Skylar. Good, great, excellent. It's really important that you're able to calculate the oxidation state of a carbon. Now, if you need more practice, of course, there are plenty of practice problems in the textbook. Now, here's another example. Say we're taking that carbonyl, and I talked about this type of example earlier on. If we took, formaldehyde, which has a carbonyl in it, we reduced it to methanol. But here we're taking acetone. This is nail polish remover, and we're converting it to rubbing alcohol, right? Isopropanol. Well, what's happening here? I'm not going to go through all the math right now. Well, maybe I will. We have the central carbon, right? We have an oxygen up here. We've got a methyl group down here, and we have a methyl group over here. Since this bond is between a carbon and a carbon, they split the electrons evenly. So 1 for each, okay? Whereas these 4 electrons, they all end up on the oxygen like this. So when I calculate the oxidation state of my carbon, I have 4 minus 2, which gives me +2. So that means this carbon is +2. I'm going to do the same exercise for my isopropanol. I have the carbon. There's a hydrogen, right? That's attached here, which is left out. I have the OH, which has 2 lone pairs on it. And then I have a CH3, and I have another methyl group over here. So the methyls, right, those are going to divvy up the electrons evenly. So 1 for you, 1 for you, 1 for you, 1 for you. The bond between the carbon and the hydrogen, the carbon is going to take both of the electrons, and then the oxygen is going to take both electrons from this bond. So now my carbon, right, is surrounded by 4 electrons. So I've got 4 minus 4 equals 0. So that means the oxidation state of that carbon is 0. So we're going from 2 to 0. That means it gains 2 electrons, right? Gain of 2 electrons, right? Think about it. Reduction is gaining electrons, right? Oil rig, reduction is gaining. So we know that the carbon is being reduced here. Overall, what happened in this reaction is that we added 2 hydrogens across the bond. So let me tell you something that I teach when I teach nursing level organic chemistry. So that's organic chemistry where we don't even look at any mechanisms, but we do talk about reactions like this one here. Something that I teach them in nursing chemistry is this. Okay, I say that in organic chemistry, oxidation is gaining oxygen, or loss of hydrogen. I tell them that reduction is losing or loss of oxygen and gain of hydrogen. So what happened here? You ended up gaining a hydrogen atom here. You gained this hydrogen atom and that hydrogen atom. So since you gained hydrogens, it is a reduction. So you can evaluate pretty quickly just by using that simple rule whether oxidation or reduction is occurring. However, you still have to be able to calculate the oxidation number of a carbon in a redox reaction. All right, here we go. Let's talk about some ways that we could make an alcohol by reduction. We can use catalytic hydrogenation. You guys remember catalytic hydrogenation, right? We looked at the hydrogenation of an alkene using hydrogen and palladium, platinum, or nickel. And we also looked at the hydrogenation of an alkyne using the same conditions to completely reduce it, or we looked at the reduction of an alkyne to make an alkene using hydrogen and Lindlar's catalyst. Well, if we take a ketone like this here, and you could do the same thing with an aldehyde, if we treat that with hydrogen and a catalyst like palladium, platinum, or nickel, it doesn't mean you put a soup in there, you just choose one of them. You can affect the reduction in a very high yield. And what I have shown here, these just look like party balloons or balloons that came from the dollar store, and that's all they are. These are the type of balloons that organic chemists use to do hydrogenation reactions. We literally just take those, and palladium usually comes absorbed on charcoal, just like the kind of charcoal that's found in a barbecue. And that's why all of these reactions that are being stirred here look like black suspensions. That's because of the palladium on top of the charcoal, where it's absorbed onto the charcoal. Anyhow, so you can see that all of these reactions are just being done using the pressure of the party balloon, which is just really atmospheric pressure is all it is. However, a lot of times if you want to do this reaction, you have to use high temperature and high pressure. Now, I don't know about you, but when I think about using hydrogen and high temperature and high pressure, or high temperature at least, I think, what if a fire was to start, right? That wouldn't be a good thing, right? You wouldn't want to do that. Now, one thing I want to point out about this kind of reaction is that if you were to, and this is a question that I've been asked students before, and it is addressed in our textbook, what if you had both the ketone and an alkene, and you did the same thing? You treated it with hydrogen and platinum, palladium, or nickel. Okay, we'll just choose palladium. What you would end up doing is exactly what you think. You would reduce everything. Okay, everything gets reduced, and you're like, well, that's not that interesting. It's not that useful. So you might be wondering, is there a way to reduce the carbonyl selectively? And the answer is yes, there are. Anyhow, so one of the ways that we could reduce a carbonyl selectively is to use this reagent. So now I'm going to start kind of fire hosing you a little bit with new reagents. So you can use, things like 3x5 cards, or you can, maybe write a song about it or something. Anyhow, or I have a former student who made a big poster where she put all the reagents on it. So we're going to start learning a bunch of new reagents today. And the first one is sodium borohydride. So NaBH4. Now, if you're like, hey, I've seen this before, isn't that the second reagent that's used in oxymercuration, demercuration? You're absolutely right. Okay, sodium borohydride is just a white solid. It's not very expensive. If you take a ketone and you treat it with sodium borohydride in a polar protic solvent like methanol, ethanol, or water. So again, these are all polar protic solvents. Okay. You can affect the reduction. It says here in a 90% yield. That's really good. That's a really high yield. And if you're very astute, you might be asking, let's go back here. Let me just copy this reaction right here. Just give me 1 second. So I'll copy this, and I'm going to try to paste it in over here so we can discuss that reaction with respect to what would happen if you were to try the same reaction and you did it with sodium borohydride. okay? And let's just choose ethanol. It's the first solvent listed there. Well, in that case, you would selectively, reduce only the carbonyl. So you would leave the alkene intact. So that's actually a pretty interesting reaction when you think about it, right? Most organic chemists, when they're tackling, the difficult research projects that occur in 2021, they say there's two types of projects for organic chemists. There's the ones that have been done and the impossible. And nowadays we work on the impossible. But anyhow, this is a really neat reaction because you leave the alkene intact and you only reduced the carbonyl. So sodium borohydride. Notice that everything is in one step, right? The sodium borohydride is in the solvent. It's all in one shot. Now, you might be wondering, what kind of mechanism is occurring here? Well, actually, this is one of those mechanisms, sodium borohydride reduction. I'd say it's one of those mechanisms that has been studied, oh boy, Avogadro's number of times, by different scientists. And actually, it's one of those mechanisms that I would say is not completely understood. I'd say it's well understood, but not completely understood. However, for organic chemistry 1, organic chemistry 2, the class that we're in right now, this mechanism will suffice. So if I ever ask you something about the mechanism, and you do have to know this mechanism, what's drawn here, which is a pretty simple version of what occurs, is completely sufficient for our class. So what happens is you have the borohydride, right? Sodium borohydride. Sodium is nothing more than a spectator ion. I'm just going to leave it out. But if you draw, the overall Lewis structure, you have the sodium cation, and then you have the borohydride. Oops, I don't know what that is. Borohydride here, okay? So you have the borohydride, polyatomic ion, and it delivers the hydride. Remember what a hydride is, right? The H plus, that's a proton, right? That's what we call a proton. If you have H minus, you have a lone pair of electrons, and that's called a hydride. So you deliver a hydride, which acts as a nucleophile and attacks the electrophilic carbon, right? Remember, there's a dipole on that carbonyl, so that carbon is delta plus. So the hydride gets delivered to that delta plus carbon. A pair of electrons moves up on the oxygen. And then since you're in a polar product solvent, it could be ethanol, it could be methanol. Here they've shown water. It picks up a proton from that. And there you go, my friend. You have made an alcohol. So that is the mechanism, and you need to know the mechanism, okay? It's not something that I'm just talking about for fun, okay? Something that's really cool about this is, let's say you have an unsymmetrical ketone. What does that mean? Well, if you look at this ketone here, this is called butanone. Here we have a methyl group. Here we have an ethyl group. That's not symmetrical, is it? There's no plane of symmetry, no axis of symmetry, I should say, in that molecule. Well, since this carbon, okay, let me use my blue pen. Since this carbon is sp2 hybridized, it's trigonal planar, right? What does planar mean? It means it's flat as a pancake. So that means that since that carbon is planar, the nucleophile, which in this case is the hydride, can come in and attack from either face of the molecule. And so you end up with a mixture of enantiomers in this case, okay? So you end up with a racemic mixture here, right? The hydride is not going to discriminate towards either face of the molecule. So that deals with the stereochemical stereochemistry that you have to take into account with sodium borohydride reduction. Well, I promised you a third way to reduce a carbonyl, and that third way, so first we looked at hydrogenation. Next, we looked at reduction using sodium borohydride in methanol, ethanol, or water. And the third one is using lithium aluminum hydride. This over here is a can of lithium aluminum hydride, LiAlH4. Now, lithium aluminum hydride, you notice it's in this airtight can. So this is actually air, over here. We'll call it O2 tight. Okay, it's airtight. Okay, and that's because lithium aluminum hydride is more reactive than sodium borohydride. So you want to keep it out of the air as much as possible. Anyhow, lithium aluminum hydride. Let me just get into the some of the semantics here. Sometimes we just spell it out like this: lithium aluminum hydride. You'll see it oftentimes abbreviated as LAH. Organic chemists are hooked on acronyms. Okay, organic chemists are, just that particular type of people that can't get enough of acronyms. And if you think about it, all we're really trying to do is get the maximum amount of work done for the minimum amount of effort. So something I want to point out to you here is that lithium aluminum hydride reduction is a two-step process. The first step is just a combination of, and here they're showing an aldehyde, just a carbonyl containing compound, with lithium aluminum hydride. And then after the reaction is complete, you add water. So remember, this is a two-step process. If you were to combine the lithium aluminum hydride and water, that would not be good. I'm not sure exactly what would happen, but I think it would be exothermic enough to make a fire. So I would be very careful about doing that. In fact, if you use excess lithium aluminum hydride, let's say, and I've done this many times in my life, and you add, you want to add water once the reaction is complete. Let's say you followed this reaction by thin layer chromatography, and you say, okay, well, now I'm going to add water. Well, if you added an excess of lithium aluminum hydride, let me tell you, my friend, when you add this water, you'd want to do it dropwise, right? You'd want to do it very carefully to avoid any exotherm that might happen. Anyhow, there we go. So it says here lithium aluminum hydride and sodium borohydride, in case you haven't noticed, are structurally similar. If you look at the Lewis structure of the aluminum hydride polyatomic ion, you see that it's very similar to the borohydride, isn't it? It's only the central atom that differs. Boron and aluminum are both in group 3A in the periodic table. Anyhow, the thing that you got to remember, though, is lithium aluminum hydride is much more reactive than sodium borohydride. It's a stronger reducing agent. Okay. Now, if you're wondering, why is that? Well, we could sit here and debate that, and it doesn't cover it in our textbook. It's got something to do, I think, with the fact that the lithium cation is a stronger Lewis acid than sodium, which it actually kind of interacts with the lone pairs on the carbonyl and renders it more electrophilic. And if you're like, what are you talking about? Exactly, right? It's something that's not covered in our textbook. However, that is one of the effects, and there are other effects based on the difference in electronegativity between the boron and aluminum. I'm not going to ask you about that, okay? I'm not going to ask you. Give me an essay. Dear students, please write Mr. Dion an essay as to why LAH is more reactive than sodium borohydride. Not going to happen. However, you do need to know that lithium aluminum hydride is a much stronger reducing agent. And what you're going to see in a few minutes is that sodium borohydride can reduce ketones and aldehydes, okay? Whereas lithium aluminum hydride can reduce ketones, aldehydes, carboxylic acids, and it can also reduce esters. So it's a more powerful reducing agent, and we'll take a look at that in a few seconds. All right, now you might be wondering, well, Mr. Dion, you showed me the mechanism for the reduction of a carbonyl, of an aldehyde or a ketone using sodium borohydride. What's the mechanism for lithium aluminum hydride reduction? Well, I got some good news, my friends. It's pretty much the same thing. If you go back a few slides and you look at that mechanism of the reduction using sodium borohydride, what you'll see is that it's virtually identical to this. The only difference is that you swap out the aluminum for a boron. That's it. Okay, so you have a dipole in your carbonyl, right? We know that this carbon is delta plus, right? Of course, our oxygen is delta minus. The carbon, we call it electrophilic, right? So we have the nucleophilic attack by the hydride, right? That's a hydrogen with a lone pair of electrons. So it attacks that electrophilic carbon. Carbon cannot have 5 bonds, and so we break the pi bond. We put a pair of electrons up on top of the oxygen to make the oxygen with a negative charge. And then we do a proton transfer, right? Remember, this would occur in the first step, right? This is just the addition of the LAH. And then this would be the second step, right? The addition of water. So it's 2 distinct or separate steps. It even says here in my notes that the proton source, the water, has to be added after the carbonyl is reduced. Now, I said this earlier, but just to remind you, if you're wondering, well, how would I know once I'm at this point, right? Well, you would monitor the reaction using TLC. You could use TLC. You could also use mass spectrometry to monitor that. You could use NMR as a means of monitoring the reaction, right? TLC is cheaper. You don't have to buy an NMR that costs hundreds of thousands or tens of thousands of dollars. You don't have to buy a mass spectrometer. But you can also use what's called LCMS or GCMS. And these are mentioned in our textbook. That's liquid chromatography mass spectrometry or gas chromatography mass spectrometry. So you see that organic chemists have developed all kinds of different ways to monitor reactions. Anyhow, that's more of a lab thing, but still important for us because we do talk about MS and NMR in organic chemistry too. All right, so as I was mentioning before, now this is something that I mentioned a few slides ago. I said, if you have an alkene and a carbonyl in the same compound and you just treat it with hydrogenation conditions, you're going to blast everything, right? You're going to reduce the alkene, you're going to reduce that carbonyl. But if you want to selectively reduce the carbonyl only and leave that alkene intact, let's say you wanted to do a reaction with this alkene. Come on, I mean, give me an alkene. That's a, you know, you're like, I spent the whole chapter learning about alkene chemistry, Mr. Dion. Absolutely. So now that alkene is intact and you could do a reaction there. And so in order to do that, you've got a couple of choices. You've got sodium borohydride and methanol. You could also use ethanol or water as the solvent. Or you can use the two-step process, lithium aluminum hydride, followed by addition of water. Now, this brings up a question that some of you might be asking, Mr. Dion, why do I have to learn multiple ways of doing the same thing? Well, that's a good question. And the answer is, they call it research for a reason, right? Because you usually don't get it on the first try. You know, when an organic chemist is trying to develop a new drug, let's say a new medicine, or synthesize a natural product, a molecule that was isolated from, maybe a plant or something that nobody has ever done before. Well, if nobody's ever done it before, that means you're the first person to do it, right? So let's say you're trying to do a reduction of a carbonyl, and let's say you try sodium borohydride reduction and it doesn't work, or it gives you a really poor yield. What would you do? You would try, the next thing that you got, on your plate, or the next thing that, and we call that sometimes the organic chemist toolbox. You'll hear organic chemists refer to their toolbox. And all that means is that the number of reactions that she or he has in her brain, right, has memorized. Now, of course, nowadays we have electronic databases that can keep track of all these different reactions, but you can't just get hired somewhere as an organic chemist and be like, let me look it up. I'll look up everything. No, you have to be able to have a lot of reactions kind of at your fingertips that you can come up with and discuss in a meeting, maybe with other people. Anyhow, so there we go, reduction. So you've learned a couple of new reagents to affect reduction. Well, the truth is this, is that it says the reactivity of hydride delivery agents can be fine-tuned, and by using derivatives with different R groups. So really, that's kind of the free market at work here. There's all kinds of different reducing agents available on the market. It says here that the R groups can be alkoxides, they can be cyano groups, they can be sterically hindered groups. There's a whole bunch of different reducing agents out there on the market. Now, if you're like, are we going to learn them all? No, we're not going to learn them all. But one that does come up later on in this class is this one, NaBH3CN. So you replace one of the hydrogens with a nitrile, and that's called sodium cyanoborohydride, right? A cyano, sodium cyanoborohydride. It's used to synthesize amines. So later on, when we get into amine chemistry, we're going to see this reducing agent. So again, chemists are even now working on new reducing agents that are good for different situations. And so, yeah, kind of an interesting area there. There's probably still people, working on research on these and developing new new methods for reduction all the time in organic chemistry. Again, the only ones that you need to know so far are sodium borohydride and lithium aluminum hydride. Well, something that I told you earlier is that lithium aluminum hydride is stronger, right? It's a stronger reducing agent. So lithium aluminum hydride is also strong enough to react or reduce carboxylic acids and esters, whereas sodium borohydride, it says generally not. And what do we mean by generally? I mean, there's probably exceptions to that, but generally speaking, I would not go to the cupboard and grab some sodium borohydride if I was trying to reduce an ester, okay? The difference is when you want to reduce a carboxylic acid or an ester, it's still that same two-step process, but now you have to use an excess. Okay, you need more than one equivalent. If you've ever been confused about what I mean by excess, instead of like a 1-to-1 stoichiometric ratio, remember things like limiting reactants and balanced equations? Yeah. Well, instead of just a stoichiometric ratio, you add more than enough. Okay, you might add double the amount or triple the amount. And you're like, well, that's kind of cool because then I don't have to weigh it out carefully. And you'd be absolutely correct, right? You can just waste all the material you want, right? Anyhow, so when we reduce a carboxylic acid or an ester, what do we get? We make a primary alcohol every time. And you remember last class, we talked about the difference between a primary, a secondary, and a tertiary alcohol. So you take a carboxylic acid or an ester, first step, treat it with excess LAH, monitor the reaction. Once it's complete, second step, you add water and you produce a primary alcohol. What can you do with an alcohol? Well, that's what the chapter is about, right? We're going to learn all kinds of cool reactions with alcohols. Now, if you're wondering about the mechanism, it's shown here. Let's take a peek at it. It's a mechanism. When I say a peek, I mean, you need to know this mechanism. But look, the first step is what you saw before. Just that nucleophilic attack by the hydride on the electrophilic carbon, right? Now you got two dipoles, right? You got a dipole going this way and a dipole going that way. But you end up with this really interesting intermediate. Okay, this alkoxide, this alkoxide, and then you end up losing an alkoxide. That's your loss of leaving group, right? You end up losing negative OCH3 or losing this methoxide. Now, is it just me or is that not, generally I don't think about that as being a tasty leaving group, right? It's the conjugate base of methanol, which isn't a strong acid. But the reason why, and I allude to it down here, it says methoxide is not a good leaving group. However, here it does act like one. Why? Because this is such a high energy intermediate. Okay, so we'll call this does it refer to it here? No. This is a very high energy intermediate. Okay, and so it expels that methoxide. Then you make an aldehyde in situ or in the reaction mixture, which gets reduced again. So this part here was the same reduction that we already saw with lithium aluminum hydride. So it's just the first step, the first nucleophilic attack, loss of the methoxide in this case, because it's a methyl ester. And then, you do a second nucleophilic attack. This is another mechanism that I want you to know. This is an important mechanism for organic chemistry 2 students, right? And knowing is half the battle, right? At least that's what G.I. Joe said. All right, let's take a look at an example here from our textbook. It says not only predict the major product, but draw a nice mechanism. Okay, well, I think that would really help us in our understanding of these reductions. The first one is a reduction with lithium aluminum hydride. So we could start by drawing the aluminum hydride polyatomic ion, AlH4. Make sure to put the negative charge here on the aluminum. So again, just pause here for a second. I'm not going to ask you about this, but if you're wondering, the lithium cation can complex with the oxygen here that renders the carbon even more electrophilic anyhow. So that's one of the differences in the reactivity between sodium and borohydride and lithium aluminum hydride. Anyhow, let's get into the mechanism that you need to know. We have our hydride being added here like this. So this is the first step of the reaction mechanism. Let's draw the intermediate that's formed. We have our 6-membered ring. We have a methyl group here. Then we have a carbon. We've added a new hydrogen. Okay, and we have this alkoxide up here. And if you wanted to, I could even color code this really. We could put a green in here, okay? And then we could put a green in here to show that that's where that proton came from. And our book actually does this. If you read the textbook before coming to class today, you'll see that the author of our textbook, David Klein, he actually color codes the hydrogens so that you know where each one came from. So now if we look at the second step, okay, in the second step, we have our water molecule. And why don't I highlight this one in red? So we have our water molecule like that. And then we abstract this proton like that. This step is actually reversible anyhow. And then we end up over here. There. And we end up with our oxygen here. We have one hydrogen here. We have this one in red. That's the one that came from the water molecule. And then we have this one in green that came from the aluminum hydride polyatomic ion, Okay, so it's really important that you understand where these protons came from, right? There were 2 protons added in the reduction, but it's important that you know where each one came from. Something that the ACS loves to do, and your final exam will either be an ACS final or an ACS-like final written by yours truly. What they love to do, and I'll just tell you this kind of quickly, is instead of H2O, they'll say D2O, right? And so you need to know that if you were using deuterium uh, oxide, you'd end up with, which we call heavy water, you'd end up with the deuterium here, right? Same kind of rationale. Anyhow, let's delete that for now. Okay, let's take a look at the next one. The next one's kind of a cool one because it's one of those examples where we have a ketone and we have an alkene in the same molecule, but we know that when we treat this with sodium borohydride, I'll draw my polyatomic ion down here, my borohydride, I'm going to get the nucleophilic attack like this, and then I'm going to end up producing that alkoxide, aren't I? So let's draw that out. I'm going to try not to take up too much space here. So we end up with this alkoxide like that. And then methanol is already in the reaction mixture. So let me draw the methanol. I'll draw it in blue. So there's the hydrogen from the methanol. And then we're going to abstract that like this. And then we end up with the final product. And there we go. And then we'll draw that one like that. And there you go. So lithium aluminum hydride reduction, 2-step process. And sodium borohydride reduction, 1-step process. Remember, instead of methanol, you could also use ethanol, or you could use water. Either one works. And if you're wondering, like, are there other solvents you could use? Probably. However, they're not discussed in our textbook. All right, let's move on to section 12.5, which deals with diols. Yes, diols. We actually looked quite a bit at diols earlier on when we talked about the syn addition of hydroxyls to an alkene, an anti-addition, and we're going to take a look at those again in the next slide. But a diol is named by using the same method that we used for an alcohol, except this, we don't drop the E at the end of the alkane, and we use the suffix diol. So here, let's think about this. If you had 1, 2, 3 carbons, what's that? That's propane. Everybody knows that. If you have 1, 2, 3, right? If you have a hydroxyl here, this would be 1-propanol, right? You drop the E. However, if you had propane here and you put a hydroxyl on carbon 1 and 3, then you have 1,3-propane diol. All right, let's say you have hexane. You've got 1, 2, 3, 4. Sorry, I'm numbering from the wrong side, aren't I? Let's do it over here. 1, 2, 3, 4, 5, 6. So that's 1, 2, 3, 4, 5, 6, like that. This would be 1,5-hexane diol. Sometimes we use the word glycol to describe a compound that has 2 hydroxyl groups. A common example would be ethylene glycol, which is used as an antifreeze. So if you've ever, had your engine overheat maybe or something, or you had to replace the coolant in your engine, you want to make sure to put ethylene glycol in there. Why? Because ethylene glycol serves to increase the boiling point, and it also decreases the freezing point of the liquid that's inside your radiator, so it'll prevent your engine block from cracking. Anyhow, I won't go into it any more than that. Although a show that I got into a couple of years ago, and I'm sure that some of you have seen this television show, is called The Forensic Files. They're always talking about GCMS or, anyhow, or ninhydrin stain, where they're looking for fingerprints and things. And, there's a few episodes of that television show where they mention ethylene glycol, where people have been poisoned using ethylene glycol or by ethylene glycol. And the reason why is because ethylene glycol actually has a sweet taste. I don't recommend trying to consume it, but it has a sweet taste, and so it can be put in a person's food, and then they would consume it, and it's a poison. However, now they put bittering agents in ethylene glycol, and so that prevents, children from ingesting it because it does taste sweet, just like glycerol also tastes sweet. Anyhow, let's move on from there. So how do you prepare a diol? Well, one way would be from a diketone, wouldn't it? or even a dialdehyde, right? You could do the same type of thing because we know that we can reduce a ketone to a secondary alcohol. We could reduce an aldehyde to a primary alcohol. You know, how could you make a diketone like this? That would be a good question for your next quiz. You know, where does that come from? If you started out with 1,2-dimethyl cyclohexene, this molecule right here, right, what would you do? You treat that with ozone in the first step, and in the second step, you treat it with dimethyl sulfide to make that, right? You guys remember, you end up breaking this bond here. Anyhow, so we could take that diketone and we could reduce it using hydrogenation conditions. We could reduce it with lithium aluminum hydride followed by ethanol, methanol, or water. We could reduce it using sodium borohydride and methanol. So 3 different ways that we have to reduce that diketone to make that diol. Let's do a little review. If you're overwhelmed with new reactions, let's get into some oldies here. We looked at a bunch of different ways to make diols when we did the chapter on alkenes, right? We said, okay, well, if you take an alkene, this is just cyclohexene, and if you treat it with MCPBA or a peroxy acid followed by aqueous acid, what do you make? You make a trans diol, which proceeds through anti-dihydroxylation. If you treat it with osmium tetroxide and N-methylmorpholine N-oxide, that's NMO. You probably haven't seen that structure since Organic 1. You do it as syn-dihydroxylation. I did an interview a number of years ago. I walked in, you know, and they were going to ask me some questions about organic chemistry. And I think the first thing that they asked me to kind of get my blood pressure to lower, because I was pretty nervous, they said, let's talk about diols. You know, how many different ways can you come up with to make diols, Mr. Dean? And I was like, well, you know, let me show you here. So I sat down and showed them a bunch of ways that I knew how to do it. So making a diol, very important that you know how to make a diol. So again, you could reduce a diketone, or you could do the same thing with a dialdehyde. Or you could do a dihydroxylation, like we saw in the alkenes chapter. So some really good chemistry that you need to know. Okay, so what have we learned so far today? We've learned hydrogenation of a carbonyl. We've learned the reduction of a carbonyl using sodium borohydride. We've learned the reduction of a carbonyl using lithium aluminum hydride. We've learned that sodium borohydride can reduce aldehydes and ketones, whereas lithium aluminum hydride, LAH, can reduce aldehydes, ketones, carboxylic acids, esters, and we've looked at the reduction mechanisms for the reduction of an aldehyde, ketone, carboxylic acid, and an ester. So we've covered all those, and then we've also reviewed a few reactions that we saw in Organic Chemistry 1.